Floor is yours.
Okay, thank you very much for this nice introduction. I just want to give you some, let's say, insights about our recent work regarding ice clouds models or ice clouds as seen from a more mathematical point of view. And as you see here, this is the topic. So this is the only photograph I have in this talk. So this is more or less the object we are kind of investigating. So, or let's say, put it this way, why should we do so? Why we are interested in ice clouds? Well, I mean, so from a theoretical point of view, ice clouds are really interesting, complex or multi-scale systems, and some processes like nucleation or so are not really understood yet. And on the other hand, the radiation effect is not clear, so even the sign of the net effect is not really fixed right now. And I mean, you can see that if you're talking about these things here, and this is a kind of a diagram with phases of ice. So you have the hexagonal ice and maybe other things. So this is really a complex situation. And on the other hand, you see this radiation effect. And in principle, there's a need for better understanding. So, and one of nice tools or nice things in the toolbox are reduced order models, where we can try to understand the basics of the system without too many details. So on the other hand, why using dynamical systems, which are systems of ordinary differential equations? Well, you can use it in two different ways. So for instance, you can try to derive simple or reduced order models for just a conceptual understanding. And on the other hand, cloud models are kind of dynamical systems because they are the right-hand side are reaction rates. So if you think about bulk models, you immediately are in the world of dynamical systems. And on the other hand, the theory provides tools for qualitative analysis of such systems. And you know all this because you know probably the famous Lorentz system, which was published in 1963 about idealized convection. So this is more or less the system here. And this is what you always see, these kind of strange attractor. So this is more or less one of the famous things of producing an irregular or chaotic system. There are many other dynamical systems or minimal models in atmospheric physics. They are just examples I list. So this list is not exhaustive at all. So for instance, there's this nice model about the variability of storm tracks. This is Martin Anbaum and Novak did some work on this. There are lots of models for aerosol cloud precipitation interactions in stratocumulus clouds. This is work by Koren and Feingold and others. There's, for instance, convection parameterizations on the basis of a predator-prey system by Hans Graf and Till Wagner and others. And very recently, there's this open and closed cell structure of stratocumulus, recent work by Hernandez and Glassmeyer. So there are many things, and I could list many others. So these dynamical systems or reduced order models are almost everywhere. So on the other hand, you can formulate the cloud processes via the ordinary differential equations, and you can do this in two ways. The first is the more consistent or mathematical point of view. You formulate a population balance equation. I will show you what I mean with this, and derive equations from the general moment procedure. You could also kind of guess rate equations for averaged quantities like the number concentration and mass concentration as you do for chemical reaction equations. And this is where you end more or less. So you have a kind of time derivative, which is balanced by a vector field. And you have some kind of variables, the number concentration, the mass concentration, the supersaturation, whatever you like. And this dynamical systems framework provides tools for describing a model qualitatively. So for instance, you can think about steady states or equilibrium states, which is just the right-hand side is equal to 0. You can think about limit cycle behavior like oscillatory things, domain of attractions, symmetries, and so on and so forth. And of course, if the dimension of the dynamical systems is increasing, the degree of complexity is also increasing. So even for three-dimensional systems, it's really hard to define or to get the limit cycle behavior in a right way. just to show you what I mean with this kind of limit cycle things, because this will play a role in the ice cloud models. So think about this classical predator-prey system. So you have a prey, which is the X, and interaction with the predator, which is the Y, is not in benefit to the prey, but in benefit for the predator. And the prey will grow exponentially if there's no predator there, and the predator will die out if no prey is there. So this is more or less the system. And you end up with a fairly nice time evolution, namely that you have some kind of oscillation here. So for instance, you have first prey, which is growing, and then predator kicks in and prey is reduced, and so on and so forth. And if you think about the phase space, the projection, you see this kind of closed curve, and this is a limit cycle. So this oscillatory behavior, which is more or less the projection of these two variables into one plane, this is what I mean with this limit cycle or undamped oscillation. You could have it also in a different way. So this is an example from cloud physics. This is this famous Wacker model from 1992, that you have cloud water and rainwater, and the cloud water is of course growing by condensation. You have autoconversion, which is reducing the cloud water but increasing the rainwater, and you have also accretion. So collision between cloud and rain makes a rain, and the rain of course falls out. And if you think about this here, under certain conditions of these A and C parameters, you end up with a kind of fixed point, with an equilibrium point. So you really go this way until you reach at some point, namely at infinite time, you reach this fixed point. So, and this is a different behavior. So this is an equilibrium point. So, and there's lots of these models for cloud states in these bulk models. So there's this work by Ulrike Wacker during the 90s. There's Thomas Hauf did some work. We did recently some things for liquid clouds, for formulating a general cloud model and investigating this. And the usual goal for these things is to understand the qualitative behavior of these cloud models, to try to reduce the complexity, so which processes are relevant and which are not, maybe deriving further minimal models from these more complex models, and finally, and this is nothing I will talk about today, to extend these things for partial differential equations for spatial structures. But here we are just talking about, let's say, point models, partial models, which can be described by ODEs. So in this talk, I will just give you a derivation of a quite simple ice cloud model and with an analysis of the model with dynamical systems. We will have some comparison to the measurements, and I try to convince that even the model is super simple or quite simple, it does not compare too badly to the measurements. And the last part is a bit more general about possible hierarchies of ice cloud models, thinking about more complexity, more reduction, and so on and so forth. The first three parts are based on this recently published article by Hanna Bergner and myself in Chaos, and it's open access. So we start with a population balance equation. This is more or less a concept board from mathematical biology. You have a mass distribution in a 3D space, and the distribution, this F, is depending on time and space and on internal coordinates M, which could be masses or something like whatever, some properties. And you transport this with a velocity in the physical space. So you have the flow velocity and the terminal velocity of the particles, for instance. And you have also a growth law. So you have mass rate, which means you have a velocity in mass space. And on the right-hand side, you have sources in six. This is a very, very general concept. And this can be nailed down to the simplest case that you have just particles of one type. So you have just one mass. Then you use continuity equation, and you end up with a version of this population balance equation. So you have, of course, the transport here. You have the growth laws. And here you have sedimentation and sources and things. And of course, this population balance equation must be coupled to some transport equations like Navier-Stokes and something like that. So this is not part of this talk here. So we have just given transport wherever it comes from, namely mostly vertical updraft motion, which we prescribe. And then you can formally go to general moments, which are just the integral over some powers of this mass times the mass distribution, and you can integrate over this, leading to the so-called moment equations. So in fact, what you have is, so here you see the transport part. This is the growth part. This is sedimentation. This is also the sources and sinks. And in the end, you have equations like this. Either you think about the Lagrangian point of view or the Eulerian point of view. In any case, you have balance. This transport or this time derivative is balanced by sources and sinks of this capital GK. And in principle, the population balance equation is equivalent to infinitely many moment equations for some type of distribution. So for instance, if you start with a gamma distribution or something like that, then it's equivalent to think about a population balance equation or all the moment equations. And of course, we cannot use infinitely many equations of moments. So we have to use a closure to get a finite number of equations. What we usually do is we fix the type of the distribution, which is kind of, well, discussable. And then we normalize also the distribution by the number concentration. So the zeroth moment is the number concentration. The first moment is the mass concentration. And this is usually what we use. And this is a classical double moment scheme. The issue is cloud processes certainly change the type of the distribution. If you think, for instance, about evaporation, the complete type, really the type of the distribution is changing completely. And on the other hand, we think about log normal distributions or gamma distribution and so on. And these are analytical distributions which extend to infinitely larger masses, which is also not true. But the nice thing is they have analytical expressions for the general moment. So therefore, this is a good reason why we should use them. Well, maybe this is a good reason. Okay, this is what we usually use for the ice clouds in the cold environment. We often use a log normal distribution, which looks like this. So you have a geometric standard deviation. You have something like a modal mass, which is translated to the mean mass. And if you derive general moments in this procedure, you are sure that this integral converges for k larger than 0 or larger equals 0, and we end up with something like number concentration times mean mass to the power of k, this is the kth moment, times weird factor, which is just given by the width of the distribution. And what we usually do, we close the system by a constant value of this R naught. And then you have number concentration, mass concentration, and of course the mean mass. So what do we need for ice cloud models? We need nucleation, so generation of ice crystals. We need growth on evaporation, which is driven by diffusion of water vapor. You have aggregation, which is not so important for cold ice clouds. We need sedimentation and sources and sinks of water vapor. And of course, this is driven by saturation ratio, which is just given by the partial vapor pressure and the saturation vapor pressure, or you can translate it with the total mass or the specific mass of the water vapor times pressure divided by the saturation pressure. And it's a nice linear quantity. So if S is smaller than 1, then the ice mass evaporates. S equals 1 is equilibrium. S larger than 1 is a supersaturation, so the ice mass will. You can use the saturation ratio as a proxy for changing temperature and pressure, or put it in a different way. If you think about changes in temperature just by adiabatic changes, you can see that they are driven directly by the vertical velocity. The same is true for changes in pressure. And if you then think about the change of the supersaturation ratio with time and write up the total derivative, you see you have the temperature change, you have the pressure change, you have the liquid, the ice mass change. And this is, if you insert all these things, you end up with a constant, just depending on pressure and temperature times velocity times saturation ratio and Gauss law, more or less. And this will be used as a proxy because we, at some point, we will stick to a constant temperature and pressure system, which is a kind of suspicious, but nevertheless it works. And we just see the change in the supersaturation driven by vertical velocity. So what we need is nucleation process. We are sticking with the low temperature regime, so we have only ice and water vapor. And we think about homogeneous freezing of aqueous solution droplets. So you have a small amount of anorganic substances like sulfuric acid, ammonium nitrate, something which is around in the upper troposphere. And then you have a stochastic process with a nucleation rate for the probability of the freezing event. And these small haze droplets or aqueous solution droplets just freeze with a nucleation rate, and you can, this is recent work, you can formulate the nucleation rate like this, an exponential function with very, very steep, let's say, increase and a kind of threshold. And this is a formulation we will use later. On the other hand, you have growth or evaporation of ice crystals by diffusion of water vapor. You have also heat conduction. If you are more interested in the mathematical details, you can see this as a coupled system of two PDEs with an ODE as a boundary condition, and this has a unique solution. I will not talk about this. And in the end, you have a mass rate equation where you have the capacity, which is more or less the ice crystal shape. You have the diffusion constant, the kinetic correction, the latent heat release, and a ventilation correction. And the ice crystal shape determines the capacity. So these are the different parts in the mass rate. And of course, at some point, if you have really small ice crystals, you think about a kinetic correction. And if you have really large ice crystals, you can think about ventilation correction because of those wakes in the turbulent wakes or flow around a particle will enhance the growth. And of course, we have sedimentation. For the terminal velocity, we often use this kind of formulation that you have a kind of saturation. If the particles become too large, you end up with a constant terminal velocity. We have also aggregation, but actually for this cold environment, the sticking efficiency is too small and we have too few ice crystals that aggregation is not really an important process. So we will skip this at some point. And here we are. So this is the classical two-moment scheme with the number concentration, the mass concentration, and the supersaturation, which is balanced by a cooling, so a source term, nucleation terms, growth and evaporation terms, and sedimentation. This is more or less what we have. And now we can think about simplifications. So first of all, we have a Lagrangian point of view. So we just move with this parcel. And still sedimentation is a partial differential equation. So this is not really nice because we want to live in the ODE world. So what we do is we just discretize this with a flux from above and something which falls out. And this simplifies the system to ODEs. We have no extra equation for temperature and pressure. We just have a constant pressure and temperature. We neglect the aggregation and we have a supersaturation regime only. So we have just an upward motion and no evaporation. And so on. So still we want to have it more simple. We have no kinetic correction because it's too fancy, no ventilation, and we neglect that during nucleation we have some mass, which is really small. Our crystals are just spheres, so it's super simple, which reduces the growth law to something like this. We have no corrections for the terminal velocity, so we have just more or less the Reynolds or the classical drag of a sphere. And we assume for the flux from above that some part of the ice crystal mass which are falling out are falling in on the top. And you can describe this by a so-called sedimentation factor. And for convenience, it will be turned in this way, that you have a parameter here with f equal 1. So everything is falling out, nothing is falling in. And f equals 0 will be nothing is falling out. And we have a fixed layer thickness of the parcel. And here we are. So this is our system. So we cooked it down to a really kind of simple system, but it's still kind of complicated. You have still the cooling term, you have the nucleation term, you have growth terms, and you have sedimentation terms. So this is the F parameter. So if you have F equal 1, so you have a box, nothing is falling in, everything is falling out. And you realize that all these parameters depend on pressure and temperature. The right-hand side has a singularity, so it's not so nice. It has an explosive term, so it's very, very steep. You have some stiff terms in terms of numerics, so you have something like this here. It's a highly nonlinear system. Just look on these exponents here. And numerically, it's not nice. So it's really challenging if you want to do it correctly, so really quantitatively correctly. But if you think about just the quality, it's fine. And this is how it looks like. So if you think about, you have an updraft with just 1 centimeter per second at a certain temperature, which doesn't change, you see that you have a nucleation event, and then the ice crystals fall out, and another nucleation event, and so on and so forth. And you end up with something like an equilibrium point. Same for the mass concentration, same for the saturation ratio. If you enhance the vertical velocity a lot by 2 orders of magnitude, you have more or less the same story. A huge nucleation event at the very beginning, but then you have these kind of tiny nucleation events, number concentration, mass concentration, supersaturation. And you have more or less the same situation here. If you go in between with 10 centimeters per second updraft, you realize you have something like an oscillator. Remember this predator-prey system. So you have a nucleation, ice crystals grow, fall out, next nucleation, and so on and so on. So in any case, you have a nonlinear oscillator, either damped or undamped. This is what you get from the system. Now you can do a little bit of mathematics and can think, well, what about these equilibrium points? So it looks like this, so here I put this equilibrium points here, but in principle for here, you see that it goes to some steady state. Can we calculate this? The answer is yes. You can reformulate the problem to just a scalar function, and you can prove that this has a unique root, and this is a unique equilibrium point. Okay, so you can prove that it's unique, that's fine. I can also calculate this. So actually what we can see is that the saturation ratio is depending just on some constants or some functions depending on temperature, but it's also depending on the logarithm of the vertical velocity and on the sedimentation factor. And you can translate everything into the number concentration and the mass concentration with some other functions, and you realize again the vertical velocity and the sedimentation factor comes into this. The funny thing is that if you calculate the mean mass, the vertical velocity cancels out, which is kind of weird because you would expect that it should change with a different vertical velocity regime, but it's not the case. And this is how it looks like. So these are nice fits, but also data just given from the numerical calculations. And you realize that the number concentration for different temperatures, so for this is 190K, 210K, 230K, you have these straight lines more or less. So this is what you get. And you can calculate these different equilibria depending on the vertical velocity. Okay, so these are the equilibrium points. This is one of the key points for dynamical systems. What is the quality of these equilibrium points? What you do is you linearize the system around these states and compute more or less the eigenvalues. And if the eigenvalues, the real part of the eigenvalues is positive, then you have an unstable system. And if the real parts are all negative, you have stable system. This is more or less like the in the predator-prey system. And what you have is you have always a negative real eigenvalue, and usually a pair of eigenvalues. So you can see it here, for instance. So this is the real part and this is the imaginary part. And for instance, here you see, so if you come through this, so you have this one negative value, you have two positive, two eigenvalues with a positive real part, but you have two different imaginary parts. So what does this mean? Well, this means that if you are in this regime, you have just a stable state. So the damped oscillator, the oscillator is damped. It just goes to an equilibrium point. If you cross this line here, if you have positive real parts, then you have an unstable case. But since you have an imaginary part here, you have an oscillating system. So this is called, and these points here where you cross in the real part, you cross the zero line. This is a so-called Hopf bifurcation. And you can translate this in a complete system or in a complete phase diagram with temperature versus vertical velocity. And if you are somewhere here, you are in the stable situation. So this is looking like this. If you're here, this is unstable. So the equilibrium point is unstable, but you have this oscillation. And if you go here, so you are again in this stable regime. And these lines here are called this Hopf bifurcation because here you have the change of the system. The theorem says, well, there should be something like a limit cycle, and you can calculate the periods of these limit cycles of the oscillation. And this is the diagram for this. So again, you see these two Hopf bifurcations, and if you cut through, for instance, at 210K, this is more or less the line you see here. This is the period of the oscillator at a certain vertical velocity. And on the other hand, this is the more or less the imaginary part of the eigenvalues, just given an additional period, or let's say a period of a system close to equilibrium. And you see a broad range of periods between 100 seconds and even 10,000 seconds. And there's another weird thing, namely that you have a kind of scaling here. So if you change the sedimentation, you just shift the diagram. So how to read this diagram here, you have to think about this line and this line here. These are the two bifurcations in the F equal 1 system. So everything is falling out, nothing is falling in. If you go to 0.1, so these are these two lines here, you shift the whole system. So here you are still in the kind of stable regime, and here you are in the unstable, so in the limit cycle regime, and here you again with the stable system. So the funny thing is you just shift the lines, but you do not change the quality of the system. Okay, now you can say, well, this is just mathematics. Come on, how does this compare to measurements? Not too bad. So this is data from Martina. With some frequency of occurrence. These dark and light blue lines is the spread of the oscillator for different sedimentation behavior. So either with nothing is falling in, everything is falling out, or part is falling in. And you realize that these lines, so this is for 200 hectopascal, this is for 300 hectopascal, we are with the oscillator, with this kind of simple model, we are in the right range. These black dots are, let's say, undisturbed nucleation events you get from, for instance, the Kerr-Lohmann parameterization or something like that, in the same vertical velocity regime. And this is the same. And of course, we are not, let's say, so I do not draw a kind of distribution here, but you see that we are fitting quite well, or we are in the right range for the concentrations. And if you go to the mass, so to the mean mass or to mean radius, which is just the same, and just plot the mean radius at equilibrium points for different pressures, you realize I would not say I fit perfect, but it's really, really robust. You see that the oscillator, which is a super simple model, it's spherical, it's no kinetic correction, all these things, super, super simple. Nevertheless, we end up with radii which are in the right range of the measurements. So from this point of view, you can say, well, our oscillator is not too bad. This kind of simple model, which was cooked down from a kind of complex situation of the population balance equation to a simple two-moment scheme, is good enough to get the right answers for, or can compare quite well with or are in agreement with the measurements. So now you can ask the question, well, first, so maybe starting with this here, how far can we go in terms of complexity? If we make the model more complex, kinetic correction, ventilation, whatever, complex shapes like spheres, like columns or something like that, how does it change? And on the other hand, you have these kind of general issues, how to derive these cloud models really consistently. So starting with population balance equation is probably meaningful, but how to derive the right-hand sides in a correct and consistent way. And maybe something else which is not touched here in this talk, but maybe this is worth to think about, on which scales are these mass distributions or general moments are really meaningful? So is it really meaningful on a let's say a meter scale, a 100-meter scale, a kilometer scale? Where is it meaningful? It's not really clear. Okay, so coming back to this in terms of complexity and reduction. So from the analysis, we usually see that the growth and the sedimentation terms are kind of very, very important processes determining the quality of the system. And in principle, you see two conceptual things. Namely, you have these growth and sedimentation terms depending on the particle properties. So you start with kind of a mass growth equation and you scale it up to many particles. And you have a vertical velocity or terminal velocity relationship and you scale it up. So it depends really on the shape of the particles and then it's scaled. On the other hand, the nucleation and the cooling terms exclusively depend on the environmental conditions. So they do not depend on the cloud. They depend on the environment. And what you can see is in a more abstract way, the growth and sedimentation terms have a general functional type like this. So the growth term is number concentration times supersaturation minus 1 times a function just depending on the mean mass. Sedimentation is the same. So the X stands for N or Q. So you have number concentration times a function which is just depending on the mass, which can be justified mathematically or physically. So in fact, you can do the same thing for a complex 3D ice cloud model. You decide about the shape of the parameters, of a shape of the particles, sorry, the terminal velocity, which is also determining the ventilation. You decide about the inclusion of the corrections, and you have more or less the same formalism. But from this, the positional growth terms and the sedimentation growth, sedimentation terms, you have a formulation for these alpha and beta functions too. And now you can say, well, in an abstract way, you can really prove when do you have a unique equilibrium state? So when do we still keep these properties? And these are just very, very simple conditions. So for instance, sedimentation divided by the positional growth must be strictly increasing in terms of mass. And if you combine the sedimentation terms, they also must increase, and also this term must increase these are for the masses, these are for the supersaturation, and then you have a unique equilibrium state. On the other hand, you can prove, well, you lose some properties if you have just a constant terminal velocity. Then you have no oscillation regime anymore. You have just a damped oscillator. And the third one, and this is not really proven yet, but there's some indications that it's good enough if you have just a nonlinear, strictly increasing terminal velocity for the particles, then you will have these oscillations. But this is not sorted out yet. So from this point of view, you can say, well, more complex models, including a complex shape like columns, kinetic corrections, ventilation corrections, still fulfill all these properties you need and have still this kind of separation between damped, undamped, damped situation. And this is just a summary of all these spheres. So I start with my basic model, which is the green line, which you cannot or barely not see here. And then I add a more complex sedimentation, a kinetic correction, and ventilation, and you realize, well, the shape of the curves change a little bit, but in principle, it's the same. And it's the same, or qualitatively, it's the same. And the same is true for columns. So yeah, of course, if you add some corrections, yeah, maybe the domains become wider or larger or smaller, but in the end, it's always the same. And this is more or less a composite of all the things we tried out. And you realize the green one, this is the basic model, is not so far away from the others more complex things. And then you can ask the question, well, 3D maybe is too complicated. Maybe 2D is better if you think about simple systems. We know that ice crystal number concentration is crucial for these ice processes, so we have to keep them. But what about the mass? Do we really need the mass? It sounds a bit weird, right? I mean, we are talking about clouds, and now I suggesting just leaving out the mass, just thinking about the number concentration. But we can try. So the first thing is we delete the mass equation. We just fix a sedimentation mass, which is more or less the same as we would use a constant terminal velocity. And we will fix a gross mass for the reduction of the supersaturation for this term here. So here is the fixed sedimentation velocity. Here you have a fixed mass here, and this is the system you have. And what you can show is that we have still the unique equilibrium states, but we have still also this damped oscillation. And it looks like this. Okay, so the order of magnitude is not so good, but the qualitative behavior is the same. So we leave out the mass equation and we are still in a kind of right regime. Of course, you have to tune a little bit with these masses, but you can have more or less the same answers. And then you can say, well, if I concentrate now just on a nucleation event, nothing about long-term behavior, just a nucleation. So the mean mass is always constant. The sedimentation is negligible because you have no sedimentation, the particles are too small. Then you end up with this toy model we played around several years ago. And this is a very, very powerful tool because in the end, we realized we can use asymptotics to find analytical solution and the model can represent nucleation events. So the dots are these, the calculations from a super complex model by Kercher and Lohmann. And the lines is our model. And this can be used as a new nucleation parameterization. So this is work by Stamen Dolapchev and Alena Kozareva during the last years, outperforming really the standard Kercher-Lohmann parameterization. So we are better because, which is unbelievable at this point, it can be used also for highly varying vertical velocities like gravity waves. So we start with a super simple toy model, but in the end, it was a super powerful tool to replace, and this is ongoing work for replacing the nucleation parameterization in the ICANN model with this really simple thing. So this is the end. I apologize a bit too late or too long. I try to convince you that this dynamical systems approach is a useful tool for analyzing these models. We find that the ice clouds can be seen as nonlinear oscillators. These simple models are good enough for representing the measurements, or the system is so robust that even not these super simple models do not fail. Well, might also be the case, but I would tend to believe that maybe the thermodynamics is correcting many things, and then this degree of freedom you have in the simple models is maybe enough to represent all this variability. We can try to derive a hierarchy of models, and even these reduced order models in 2D are well suited for qualitative or even quantitative investigations. So looking at this new nucleation parameterization, this was really a very, very exciting thing we found during the last years. So as an outlook, well, of course, I would go on with the development of the full hierarchy of the models, and it's not so easy to analyze the properties of these models. I said before that if you go to 3D, it's really, really difficult to analyze the models in a good way. And of course, what's still open is the investigation on different scales. And this is the end. Thank you.